Let us start one new topic. It is another data structure, tree. We have learned many data structures, but tree compared to other data structure unique in several respects. So, we will learn about tree structures in this module. This module includes 5 more video lectures. We will cover all the concept in tree data structures, and also we will see the programming with tree and then the JCF utility for tree in any program implementation. So, today we will cover about basic concept about the tree data structure. So, we try to understand what exactly the tree and why this tree structure, and then how these tree structures, and so basic. So, it is a basically basic concept about tree, particularly those are not from the CSE discipline. For them this needs to be studied little bit in depth, and for those are the CSE student, they can learn many more new things related to tree also. So, this video lecture basically plan to introduce the tree structure at the very beginners level. So, first we will introduce the concept of tree, and as because it is a new data structure, so many terminologies are there. So, we try to first get acquainted with those are the basic terminologies related to these tree structures, and then finally every data structure should have its own characteristics. So, tree also no exception. We will see exactly what are the different properties that the tree should have. Mainly we will discuss about a special type of tree only, which is used in theory, and in computer science is basically all about a tree, and if it is tree then only it is binary tree. It is a very surprising thing that no other tree concept is there except the binary tree. Now, there are many variations of the binary tree also will be covered in this course, but anyway basic introduction to binary tree will be covered first, and then we will try to understand how a tree can be stored in computer memory, because we know how a stack can be stored using an array or linked list, like queue also can be array or linked list. How array can be stored in memory, that we have studied. How linked list can be stored in memory, that also we have studied. Now, here also we have to study about how a binary tree can be stored. So, this is the representation of binary tree. So, this is our topics for today. Let us start first giving an introduction, the introduction to the tree data structures. Now, first of all, why the tree data structure come into the picture? Now, so basic objective of any data structures is basically to store the elements and in such a way that it can be accessed as fast as possible, and it should be also that efficiently memory can be utilized. So, there are two aspects mainly matters so far the data structures and its utility is concerned, mainly that faster access, and second thing is that better memory utilization. Now, from the memory utilization point of view, array absolutely very good, because it does not take any other extra information other than the elements to be stored there. Unlike in case of linked list or other data structure where we have to store few more information rather link like this one. But sometimes you know, so this extra storage is at the cost of extra speed actually. So, there is a speed versus memory trade off. So, array is good so far memory utilization is concerned, but operations are not so faster, because insertion deletion is a really costly affairs. On the other hand, memory utilization, if you see, sometimes say suppose your memory available, that is there in computer memory I am talking about, but not at one place. For example, you want to store an array of 1000 elements, and for this 1000 element it requires 800 bytes. Now, in your memory 800 bytes free space is available, but not at one location, that means as a single block. So, in that case the memory is available, I mean free space 800 bits quite available, but as it is not in a contiguous location. So, you will not be able to allocate a memory for the array. So, the array operation will fail. So, if it is a contiguous data structure, then fine, array you can, and then if it supports, fine, but if it is non-contiguous, then array may not be good one, and usually the memory store the data in a non-contiguous manner, rather better. Okay. So, for small data that you want to maintain, array is fine, but for larger data that needs to be maintained, then definitely array should not be. You have to give a second thought to array to represent your data, that is what. And the data usually in the real life application is very large, it is called big data like. So, tree array is really not good. So, tree is the solution. So, what is the idea about the tree is that if the elements are not stored in a contiguous location, so let it be in a whatever it is memory is available. But if you do that, then we have to have the ordering information to be maintained. We have learned about how linked list structure is used to maintain that which elements after which elements like. So, ordering is imposed there, but if you see that is in a linear fashion. So, in that sense linked list is called the linear data structures, but there is another concept is called non-linear ordering, that is sometimes very fast than the linked list operation, because in case of linked list, if you want to search for a particular element, then you have to start from the header and traverse the list one by one, and that is why the accessing operation in linked list other than the first element actually it is very costly. But here the tree is basically a solution where the fast access can be possible. We can make the faster access than any other data structure like array or linked list structure. Now, we will see exactly how it is possible using tree, and that is the strength of the tree, or what is called the plus point of the tree is that it can store elements in a non-contiguous manner, and that to be retrieved in a very fast, in a fastest way possible actually. And let us see, this is the idea or motivation rationale behind this new structure. Now, let us see first how a tree look like actually. As the name tree implies, that a tree basically is a real life tree. A tree has a root, and then it has many branches, and then finally it has leaf, and then fruits, flower, and everything is there. So, actually a tree based on the same concept, it has a root, it has branch, it has leaves, it has fruits and flowers like this one. Now, this is the typically a physical structure of, I mean a view of a tree look like. So, this is the basically root, the starting point, and these are the different branch actually you can say, these are the different branch, and these are the leaf, that is the last node actually here the end, because after that there is no more branching, it is there. And where is the fruit and flowers? So, actually each node here they are not dummy, they basically store the data. So, all elements which is stored their data, we can tell they are basically fruit and flower in this tree. So, actually we have to store fruits and flowers in the form of a tree structure, and then what is the good point is that starting from the root, finding a particular fruit or flower is very fast actually. It is not necessary to traverse the entire tree, we can have the only in which branch this fruit and flower exist, we can reach to there. So, this way we can go to that particular target elements at a very fastest rate actually. So, this is the concept about the tree, and actually physically a theoretical tree or tree of computer science looks like this as it is shown here, and this is a general tree, but there is a special tree we will be discussing in this lecture called binary tree. This is not a binary tree of course, I will see exactly what is the concept of binary tree actually it is there. Yes, this is another example, and you can see this tree stores information, and as you see here we have stored the different months of a year. These are different things, and for this different month we can store the different other elements and everything whatever it is there. And this is a particular example, you can find the difference between the two. This, although it is look like a black box, I am blank, right, but it is not blank, the tree is loaded with some elements in it. And another difference is that here every node has at most 2 branches, for example here, but here actually some nodes has more than 2 branches, some nodes have only 1 branch or whatever it is there. Anyway, so this is a particular difference, and in this context this has a special what is called the characteristics, that it is called the binary tree if it has at the maximum 2 branches. Anyway, otherwise these are the same concept actually. So, this is the idea about tree, and here is another example of tree, and you can see the difference between this tree and this tree is obviously clearly visible, because this tree stores some string or names like, but here this tree stores something else. It basically stores operator and operand. What we can say in other words is that it stores an arithmetic expression. We have also studied how an arithmetic expression can be stored in the form of an array, how an equation expression polynomial can be stored in the form of a linked list. But here is an example, this is a binary tree, how an arithmetic expression can be stored in the form of a tree. So, tree has many applications, but we can say what one the thing is that it can store any information, any type of information rather, as you wish, and also it can be stored in a non-contiguous memory location, and the tree structure is such that any element can be accessed in a fastest manner. So, this is the idea about the tree structures. Now, let us learn many more things about the tree, and so this is the concept. I will discuss about the basic the idea about how the tree can be stored in a different way, but this is a concept actually, the theoretical definition. This is a theoretical definition, as I said, about how formally a tree can be defined. So, this says that a tree is decided by a root node. Every tree should have only one root node, that is the important characteristics. All these definition to make the things more stringent for application point of view, because every should be defined in a very proper manner actually. That is why it makes sense actually. So, that is why proper definition or formal definition is required. We are discussing a formal definition here. Now, this definition says that every tree should be designated by a special node called the root node. For example, this is the root node, and then each node, whether this root node or any other node, will be characterized with a number of subtrees. For example, this root node has subtree called T1, this is another subtree, and this is a subtree. Actually, this tree has 3 branches, and each branches leads to subtree. And if you come to each subtree again is a tree. So, it is called the recursive definition, or it is a null. Okay, this is the termination condition for any recursive definition, and this makes a sense that how a tree look like. It can be as large as possible, because it can have many branches and many subtrees for each nodes, and it can be as large as possible. So, this basically tell you that tree can store infinite number of elements into it, and root is basically the starting point to access any elements in it, because there are so many nodes are there, so many elements are there, but you have to start from somewhere. So, root is the point, and this basically the concept about this is the concept that the computer scientists have decided about to define a tree, and then follow this tree in many theory, in many application and programs. So, let us learn about few basic terminology related to trees. We have the basic concept about, and a tree, this is a very old concept. I just want to see about how a tree look like this can be stored in the form of an expression actually, because expression is basically string. So, here this is suppose T, this denotes the T, and we can denote this T as a expression. The idea is that here if you see A, then it will store the subtree by the parenthesis. So, A has the subtree this is the one parenthesis, another subtree, and this is the subtree. Now, if you come to this again another tree, this has the subtree, for example, D has these elements, it does not have any other elements, so parenthesis. So, it is from the parenthesis, within the parenthesis, innermost parenthesis, and again innermost parenthesis. This basically lay down you to store all the elements, all the nodes in a tree in an expression, but it is a very pretty old concept and no more use, but it only has the important that okay, how a tree can be stored in a compact way in the form of a string only, and Java is good for handling string. So, many of you can think about that storing your tree in this type also, although it is obsolete, but still many applications like natural language processing or machine information retrieval and web page, web content storing and everything, this kind of concept it is used. Okay. So, now let us have few more definitions or terminologies related to our queue structure. First is the concept of node we have discussed. Now, here as you see, each tree is basically a collection of nodes, right. So, for example, here is node. Now, here if you see how a node can be defined, because node is node. Now, how this node can be defined? I am telling about defined means whenever you have to write a program, how a node can be declared and how a node can be defined. So, a node for a tree, I am telling about a specialty is a binary tree. Our discussion will be limited because binary tree is the ultimate tree, that is basically everybody use it, other tree does not have any implication or significance. So, any node of a binary tree is characterized with 3 elements, 3 information rather. Now, again you can recall for a linked list, it is characterized again if it is a node of a single linked list rather, it is characterized with 2 information, data and link. In case of double linked list, it is characterized with 3 information, data, then right link, left link. But in case of tree, just like a double linked list, it is characterized with 3 information. The data, it is just like fruit and flower where actual value to be stored, and it has 2 link field. This link field is basically to point the left subtree and right subtree. So, this particular link field is basically to point the left subtree, that means pointer to the another branch, and this field store the pointer to the right. So, this is called the left child and right child. Here for example, this is the one node, it has left child, this one. So, it basically store the address of this left child and the address of the right child, and every node therefore store the address of their 2 children, left child and right child, and this way the entire tree can be stored, the entire binary tree can be stored, and that is the beauty of this, right. Only simple node structure is very useful to store any data of any capacity, any size. Okay. So, this is about idea about the node information. Now, let us discuss about another, the parent. Now, every node is characterized with 2 things, the parent and its children. Now, here in this case, this is the one node which does not have any parent. This is the special node root does not have any parent, otherwise every node has their parent. So, this node it has parent and this node it has parent. So, 2 nodes may have the same parent, 1 or more nodes have the same parent like, and there are some nodes which does not have any children. For example, this node does not have any children and these are the nodes. Now, so there are some nodes which does not have any children, they are called terminal node, or leaf node. For example, A, B, C, D, E in this example is the leaf node like. Okay, now children we have discussed about node, parent and everything, left child, right child also we have discussed about. Now there is another link. Now we have already discussed that for every node rather stores two links. They are basically pointer or address to their left child and right child. The link field can be null. For example, for all leaf node, the two link fields store the null values. If a node can have only one children, if it is left children, then it has the non-null value there, and right children link value is null otherwise. So, it is the concept about link. Then root we have discussed about a special node, the root is there and root does not have any parent, and this is an example about storing the different elements into a tree. 13 nodes are stored in different order, it is little bit in order of course you can find. And then the sibling basically the two children of the same parents is called the sibling of each other. Now in this example, for example, D and E are the sibling. However, here in this example E and F they are not sibling because their parents are different. So, now this is the concept of sibling that is there in the tree, and then there are few more definitions which are very important regarding level, degree and heights. So, the root, the node is in a level called the 0 level, that then all children of the root node is called next level called 1. Then if a node is an level I, then its children are at level I plus 1. So, these are the all nodes in second level, the third level, and this is the nodes in the fourth level. So, this basically you see the every nodes they are in a particular level so far the binary tree is concerned, and the leveling starts from 0 to any value. 0 indicates that the nodes at the root level. Now here degree, every nodes has number of link or subtrees actually. So number of subtrees that a node has, it is called degree of this node. Now in this example, here this is the node. What is the degree of this node? It has 2 children. So, degree of this node is 2. On the other hand, if you come here, what is the degree of this node? It has only 1 children. So, the degree of this node is 1. But if you come to this node, what is the degree? It is degree 0 because it does not have any children. So, all nodes in a binary tree have degree in between 0 and 2 both inclusive. So, there should not be any tree in a binary, any node in a binary tree having degree more than 2 or less than 0. So, this is the concept of degree, and now let us come to the discussion about height. Now, height is basically defined as the number of nodes to be traversed in a longest path starting from the root node. Now here if we see this binary tree, this is the one the longest path. There may be more than 2 paths have the longest path also, that means same path which are large. Now how many nodes you visit? 1, 2, 3, 4, 5. So what we can say that for this binary tree, the height is 5. And one interesting correlation, as you can see here in this example also, it can reveals that height is exactly the highest level possible for a binary tree plus 1. For example, highest level is basically 4 and then height is basically 5. So, this is the just right, there is a proof also, always it is true that height of a binary tree is the highest level plus 1. Then, so binary tree is a special tree, it has only 2 subtrees that we have discussed, and all subtrees are different and unique. And one more important point that you can note is that whether node can store duplicate values or not, any node can store any values. So, in that sense you can store, but actually from the application point of view, a node should not store the duplicate values, all nodes should be unique, because it does not have otherwise any meaningful application of it actually. Anyway, so any node, logically it should not, or physically you can store any elements in it actually, but it is again homogeneous data structure like array, linked list and stack, queue, whatever it is there. If a tree is defined, then it can store in a particular type of things, it is there. So, this is the idea about the concept, and there are few variations. So far the binary tree is concerned, one complete is called the full binary tree. A binary tree is called the full if all its levels store the maximum number that is possible. Now, I am telling you the maximum number that a binary tree at level I is possible is 2 to the power I, where I can change from value 0 to the any numbers. Now, for example, the level 0, that is the root, contains 2 to the power 0 only 1. So, next level 2 to the power 1, 2 elements. So, and so on, as you can see here. So, level 0 number of nodes 1 and this is the number of nodes 2, and the last level which is level 3 and the number of nodes is 8. So, 2 to the power 3. So, you see the number of nodes at any level I is 2 to the power I in that level. So, this is a peculiar things it is there, and so a tree, a binary tree is called full binary tree if it contains maximum possible numbers in each level. Maximum possible number in ith level is 2 to the power I, that is all. So, this is a peculiar, this is another particular characteristics or property that a binary tree have. If it satisfy, then such a binary tree is called full binary tree. Now, similarly full binary tree, there is a complete binary tree. Complete binary tree just like a full binary tree, but only difference is that except the last level, all levels are having the maximum number of nodes possible in that level. So, in that sense a full binary tree is a complete binary tree, but reverse is not true, a complete binary tree is not a full binary tree. So, this is the two different what is called the nomenclature or name for a binary tree is known in the right. There are another few type of binary tree is there, it is called the skewed binary tree. As you say, as you have already learned about that a binary tree can have 0 children, 1 or 2 children, but if a particular binary tree has always all nodes contain only 1 children, then such a binary tree is called the skewed binary tree. So, there is a typically skewed binary tree. Here you can see in this binary tree all nodes have their only the right children, but they do not have any left children. Here the left children all nodes have except the leaf node of course. Now, here alternatively one children has left and then right and so on, but here all 3 trees that we have demonstrated here, all node except the last node or terminal node or leaf node has maximum 1 children of it. So, such a tree is called skewed binary tree. Now, let us first discuss about properties of binary tree. We will discuss few important properties of binary tree, and these properties are very important because it has many theoretical questions, particularly those are the students interested for GATE or competitive examination. Many questions asked from this concept, properties of binary tree. Binary tree owed many properties, very interesting properties. So, let us learn about the different properties that a binary tree possesses. And then the first property, this is basically regarding the maximum number of nodes in a level. We have already discussed about it, that there is basically theorem, we can say. Basically every properties can be expressed in terms of theorem. It is always true actually, that is why their property or their theorem it is called. So, this property says that in any binary tree the maximum number of nodes in level L is 2 to the power L, where the level can varies from 0 to any numbers. So, this is clearly visible from here, that okay, this is the level 0, 2 to the power 0, that means number of nodes in that level, to level 1, 2 to the power 1, 2, and this is basically 3, level 3, number of nodes is this one. So, this way. So, total number of nodes, that also can be counted by summing up all the number of nodes in the level it is there. So, for a full binary tree, it is basically sum of all the nodes in each level, actually it is there. Anyway, so those things is a separate issue there, but this property is very useful to count the total number of nodes that is there in a particular binary tree. Okay, so this is the first property. The second property, that is again interesting property, is that this property is related to what is the maximum number of nodes that is possible in a binary tree. Now, obviously, if a binary tree is a full binary tree, then it can contains maximum number of elements, because all levels are occupied with all elements in it, all nodes in it there. And so, maximum number of nodes that is possible in a binary tree, if its height is h, then this formula is valid, 2 to the power h minus 1. Now, that can be clearly understandable from here. So, it is basically summation. So, I equals to 0 to L, L is the maximum number of level, in this case L is 3 and 2 to the power I. So, this basically expression can leads to 2 to the power L plus 1 minus 1, and you know L plus 1 is basically height. So, that is why this formula stands as 2 to the power h minus 1. So, this is basically the formula for the maximum number of nodes that is possible for a binary tree. So, it is possible when binary tree is full binary tree. Now, if I ask you the question, what is the minimum number of nodes that is possible for a binary tree? Then that question can be answered again. So, minimum number of nodes possible for a binary tree if all levels contains minimum number of nodes. Now, all level contain minimum number of nodes possible only if it is a skewed binary tree. So, in case of skewed binary tree, if its height is h, that means the maximum number of nodes that is possible there h is there. So, if n number of nodes are there in a binary tree, its height is h or its height is n if it is a skewed binary tree, actually that you can verify again. Now, again let us continue to more properties there, and okay, this is the property that we have just now told about, the minimum number of nodes that is possible in a binary tree. It is possible for a skewed binary tree, and if n number of nodes are there, that is the maximum minimum number of nodes, it is basically h the height. So, in this case the height is basically the number of nodes it is there. Now, there is another property is the number of nodes and edges in a binary tree. Now, there is very interesting property that it holds, that number of nodes is equals to total number of edges plus 1, it is always there. Now, for example, in this binary tree, if you consider total number of nodes is 15 and total number of links or edges are there. Now these are the last leaf nodes, they do not have any edges there or links there, but all others. Now here if you see in this particular tree, this has, these are the 1, 2, 3, 4, 5, 6, 7. So this part has 7 and this also part has 7. So 7 plus 7 is 4 and then this one is the 1. So total actually here 15, total number of nodes 15 and number of edges is basically 7. Here is the 7 here and in this part is 7 edges are there. So this formula always valids. N, the total number of nodes, is equals to 1 extra than the number of edges it is there. Now this formula is also true for this as well as true for this, you can verify of your own. So this is an interesting property. Now let us see the other property, and here is the property related, that is a very interesting property and valid for any binary tree. This says that n0 is equals to n2 plus 1. What is the n0? n0 is number of terminal node or leaf node, and n2 is the number of nodes having degree 2. That means the nodes which has both children. It is always 2. Now let us come to here. Now in this example, as you can see, total number of leaf nodes, as we see, it is 8 in this node because 8 nodes are there. n0 is 8 in this example. Now let us see how many nodes having degree 2. So this node 1, this node 2, 3, 4, 5, 6 and 7. So 7 nodes are having degree 2. So n2 equals to 7 and n0 is 8. So this formula valids. Now here also you can see n0 is 1 and n2 is 0. So that is also valid for all skewed, and here also you can verify of your own that the formula is also true for any tree. Now these are the few trees I have given. You can draw any binary tree and you can verify that this formula holds good for any type of tree. So this is another interesting property that the binary tree follows. Now height of a complete binary tree. Now there is a formula. This formula again you can check it, log 2 n plus 1 is the formula, where is basically it is the ceiling. So n plus 1 its ceiling value it is there. Now in this example, for example, this is a complete binary tree, of course, the number of nodes is n. So here 15, so 15 plus 1 it is 16 and log 2 16 it is 4. So height of this binary tree is basically 4. So this is okay, fine, true for this tree. Now for this tree again we can verify, for this tree again we can verify, for this tree again. Now number of nodes is basically, for example here 3. So 1, 2, 3, 3 nodes up to this one. So here, so n is 3, so it is 3 and then 1, 3 plus 1 is a 4. Now log 2, this basically log 2 or 2, that basically log 2 is 1, so height is 2 in this case, height is okay, floor, okay, it is a 3, right. So 3 plus 1 is a 4, log 2 4 is basically ceiling of 4 is 3. So this way it is height is 3. So you can verify this formula for this tree as well as, and for any tree it valids actually. Okay, I am sorry, this formula is not valid. This formula is only valid for a complete binary tree, as this is not a complete binary tree. So this formula is not valid. So that is why we could not find the height is for this, and this is also not a complete binary tree. You can see this formula you cannot valid. So for this binary tree this formula is not valid, but this is a complete binary tree, this formula is valid, and this is also a complete binary tree. So this formula is valid. So this formula is valid only for complete binary tree. So this is another interesting property, okay, that you can have it. Now, there is another property. Okay, we will just discuss about how a binary tree can be stored in a memory. There is a two representation, linear representation, that means an array can be considered to store a binary tree. Let us have a quick idea about how a binary tree can be stored. Now, in this tree, this is a tree, there is a rule, these are the rule actually that we can follow, so that the link can be automatically mentioned without storing them actually. So, this is very good idea about that, without any maintaining the link information, but link can be ensured. What is the idea? The idea is that, okay, say index start from 1 to n in this example. So, root node is at location 1. So, always it is there, root should be stored in the first location, and then any node whose root is at ith location, its left child will be stored in 2 star I location, and its right child will be stored 2 star I plus 1. For example, this is the star, star is stored in the location 3, then its right child C will be stored in its left child will be stored in 6, it is the 6, and the right child will be in the source. So, here is the, this is the right child and this is the left child, whatever it is stored there. Anyway, so this is the idea of it is there, and so root node is 1. So, this is the right child, we can say right child is stored here in 2 star, okay, right child, this is a 2 star, right child is this one, and left child, this is the left child is 2 star I. So, this one 2 star I and its right child is there, right child is star, it is 2 star I plus 1. So, this formula that you can verify, and another important property that also you can check it, if any node it is in the ith location, then its parent can be tracked at this formula, it is basically floor of I divided by 2. For example, this is stored in 7th and I divided by 2, 7 by 2 means 3.5 and floor value is 3. So, it root is in the third location. So, it is the root location, as you see I's root location is this one. Now, following this mathematical formula, you can check for any node in this tree can be stored this way, and this is the entire array that is required to store this one. Now, this is very important one observation. Here you see automatically the tree can be stored into an array, but without storing any linked information. That means, what is the link or link information mean left child link and right child link, or address of the left child node or right child node, it is there. Now, again that formula consider, this formula consider 1 to n and index starts from 1, but if the index starts from 0, this formula needs to be little bit modified by accordingly. So, 2 star I, this is fine, but here 2 star I plus 1 instead of 2 star I minus 1 and accordingly. So, that formula you can verify again. So, if index start from 0 and index start from 1, the formula will be little bit changed, only this formula will be changed like this one. Okay, so, this is about array representation, and here is an example about another binary tree and its array representation. Again you can check the formula that we have followed to do that there, and I should advise you to repeat the same but for starting with 0 and this one, and accordingly you can verify it. Now, here is a two more properties, that is very interesting property again. It says that what is the size of the array that is required to store a binary tree, and this formula says that the maximum size that is required to store a binary tree is equals to 2 to the power n minus 1, and this is the case when binary tree is skewed. On the other hand, minimum size that is required to store a binary tree, it is basically when the binary tree is complete, and this formula says that minimum size which is equal to 2 to the power, this is basically the height formula, 2 to the power height minus 1, log to n plus 1 this one. So, this is basically size that is required to store a size of the array that is required to store a binary tree. Now, this is the maximum, and that is the one advantage. There is a disadvantage that for a skew tree, if you want to store it, require a huge array to store it, although many location of the array remains vacant actually. Now, so these are the minimum and maximum size. Now, let us come to the linked representation of binary search tree. It is basically we have to store the pointers there. Now, here is the idea about different nodes, how the address can be stored. You can check that this tree and this memory mapping also can be readily about it. Here each nodes are there and then pointers it is there. Okay, so this is basically memory representation, and this you can see all the elements or nodes are stored non-contiguous fashion, but in case of array the elements are stored in a contiguous location. So, this is the memory representation. These are another example of linked representation. Actually it takes place in memory actually. This is basically the logical view of a binary tree when it is stored, and physical view that we have stored in the previous slide actually. So, this is the binary tree representation using memory, I mean using linked form information, and then array also we have discussed about it, and there are many more things that is discussed you can find in this book. It is very nice, it contains lot of discussion nicely, and I should advise you to go through. If you want to learn many things about the tree structure, you can find chapter 7 there. Okay, thank you. In the next lecture, we will discuss about the different operations that we can apply on the binary tree. Okay, thank you very much.